Hello, in this lecture, we're going to start with the quantum mechanics, and the approach that I'm going to take is postulatory kind of approach. Okay, uh, so we'll start straight from the business. That is, we'll start from the postulates. Okay, so this lecture on quantum mechanics is based on the postulates on which your quantum mechanics is based. Okay, so the first thing that arises is why do we actually need postulates? Okay. So one has to understand or you have to accept when you start studying quantum mechanics. And one thing that I want to tell you that the linear algebra is going to be conducted in mathematical physics. So much of the background I'm going to assume, at least BSc level of background I'm going to assume for these particular lectures. Okay. Now see, the first thing that one should understand is that uh, that 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 the uh, that the that quantum mechanics is much based on, or you can say, the formalism of quantum mechanics. Formalism of quantum mechanics is based on certain postulates. Okay, you can say, take some number of postulates. Okay, now one feels a dilemma here that on what grounds these postulates are dictated. So one can uh, understand from the birth of quantum mechanics that there were a series of experiments that led eventually to the birth of the experiments. You can understand that all of these postulates that govern the quantum mechanics are based on the experimental observations. These are based on the experimental observations. Okay, so these are based on the experimental observations. Although one should also understand that these postulates cannot be derived. These postulates cannot be derived since they are basically an outcome of experiments, cannot be derived since they are outcome of these series of experiments that eventually led us to understanding that at certain scale in physical realm, the physics behaves quantum mechanical way. Okay, so so they cannot be derived since they are outcome of experiments. Now one again feels a dilemma here, and one has to understand that how can we one very sure of how can we one how can we one how can one be sure of these postulates? So how can one be sure of these postulates? So the idea is that their direct their direct validity cannot be asserted. Direct validity cannot be asserted. Rather, an indirect way is possible. Rather, an indirect way is possible. And what is this indirect way? Okay, what is this indirect way? So, what is the idea? We have to actually build some theory. Let's say we build some theory on these postulates. So, let's say some theory is built on these postulates. And if this theory works in experiment also, if the theory works, then we can be sure of these postulates. Then one can be sure of these. One can be very sure of these postulates. Otherwise, they are not going to make sense. Otherwise, they don't make sense. So the good news is that for much of the physical phenomena, for much of the physical phenomena, we do have some answers. Physical phenomena, we do have answers. And these answers are certainly based on the postulates, and these answers are based on the theory formulated, uh, you can say, on the foundations of these postulates. Okay, so this is a slight introduction that I wanted to give you, that why these postulates are so necessary. Now, if you have certain idea of Hamiltonian mechanics, one can understand that one can remember that the most generalized sort of formulation of quantum mechanics, in most generalized formulation of quantum mechanics, the state of the classical particle, I would say, the state. Why would I differentiate between classical particle and quantum particle? I mean, I wanted to suggest that the particle whose motion or whose motional laws are governed by classical physics. So state of a classical particle is governed by two dynamical variables. And what are those dynamical variables when it comes to Hamiltonian mechanics? So these two dynamical variables are position and generalized momentum. So these are the position and the generalized momentum. So let's say R vector represents your position, and generalized momenta, you can say, is P vector as a function of time. Okay, and these the time evolution of R vector and P vector are governed by some uh, by Hamilton's equations of motion, by Hamilton's equation of motion. So the time evolution, so you can say the Hamilton's equation of motion dictate the time evolution of the I will say time evolution of the position vector and the momentum vector, which in general dictate which in general uh, you can say, I should not use word dictate, which in general tell us about the state of the system, or state of the classical system or particle, whatever suits you. Okay, and from classical mechanics, if I just use a single variable here, so if I just use a single variable, we know that x dot is given by del h upon del p, where p is the conjugate momentum, and p dot is governed by minus del h upon del x. Okay, so in Hamiltonian mechanics, we know that the state of the classical particle is governed by two dynamical variables, that is the position r vector and momentum, and the Hamilton's equation of motion dictate the time evolution of these two, that is the position vector as well as the momentum. In short, this is how your classical mechanics work. However, the quantum mechanics, you will see that there is here there is a certain sense of determinism. Here there is a certain sense of determinism. Okay, but in quantum mechanics, what we will understand and what we know from our some experience of quantum mechanics, that the approach is quite probabilistic in nature. Okay, so the question arises that how to understand about the about the quantum state at certain time t, okay, at some time t. This is the first question that comes to mind. And second question is, how does the state evolves with time? How does the state evolves with time? So for example, here you had some Newtonian, Hamilton's equation of motion. And if you're not well accustomed, you don't understand this thing, then you know from Newtonian mechanics also you can understand how does your position changes with respect to time. So basically you need some kind of law. So how, when it comes to classical system, you know that there is certain law that dictates the evolution of the system, or I would say the evolution of the position vector, okay. Similar question arises for the quantum mechanics also, that how does a quantum state evolve with time? Evolve with time. And what about different physical quantities? Like for example, we talk of momentum in in classical mechanics, we talk of kinetic energy in classical mechanics. What are all the different quantum analogs to all these systems? Okay, so we'll also learn about those things. So basically, how to assess various physical quantities. Okay, and I will strongly suggest that parallelly I would be running linear algebras. You just actually attend those lectures also, because once you attend those lectures, you will be able to understand quantum mechanics better. Okay, so here I'm going to assume a certain level of understanding that you carry from your undergraduate section. So this is what I'm going to assume. Although I will actually try to revise all the concepts, but still I would assume that you know quantum mechanics till an undergraduate level. Okay, so just a brief revision to what we have formulated. The first thing that we formulated is that we are going to take a postulatory approach. Okay, so postulatory approach in which I'm going to dictate some postulates on which your quantum mechanics is based. And I've already stated why these postulates are so important. First thing, that these derive their inspiration from the experimental observations. So there is nothing to doubt about. Okay. Also, they cannot be derived since they're outcomes of experiments, but you can be very sure of these postulates. Why can you be very sure of these postulates? Because the direct validity, although they cannot be ascertained, but an indirect way is possible. What is an indirect way? Let's say you build a theory on these postulates, and if this theory works, one can be very sure of these postulates. Otherwise, they don't make sense. And for much of the physical phenomena which are dictated by quantum mechanics, we do have answers, and we do have very satisfactory answers. Okay, so you can say one of the very you can say very engrossed kind of field in quantum mechanics is magnetism. Okay, and you know that the complete world is running around it, from hard drives to magnetic levitating trains, from superconductivity to all sort of different magnetic phenomena. Okay, and magnetism is essentially quantum mechanical phenomena. Okay, so you know that our understanding of quantum mechanics is eventually getting implicated, and one can be very sure of from these kind of you can say observations that you see. Okay, so much of the physical phenomena that we understand from quantum mechanics, we do have certain answers, and a certain we can say not certain answers, these are very certainly you can say very non-ambiguous kind of answers. Okay, so basically this is how you formulate quantum mechanics. Okay, in Newtonian mechanics, or you can say in the classical mechanics, or you can say in analytical mechanics. So basically, I have taken just an example from Hamiltonian mechanics because this serves as the best framework to understand both classical mechanics and quantum mechanics hand in hand. So I have taken the case for Hamilton mechanics. So we know that from Hamiltonian mechanics, we know that the state of a classical particle is governed by two of the dynamical variables, that is the position vector and the momentum. And you just dictate me at any point of time what is the position vector and what is the momentum. So I know what is the trajectory going to be. How you just dictate me one of these things. Okay, so I know the state of the system. Okay, so from just knowing R and P, I know the state of system at any time t, And this particular evolution can be understood from the Hamilton's equation of motion. So there is a certain sense of determinism here. However, in quantum mechanism, probabilistic interpretation takes a you can say uh, uh, takes a driving seat. Okay, so in quantum mechanics, with regards to state of the system, you cannot say anything with quite determinism. You are going to say anything probabilistically only. Okay, and this brings us to certainly three of these questions, which are analogous to the classical formulation that we've studied. That one, how to understand about the quantum state at any time t, how to understand how does this state evolve with time, that is, what is that law or what is this equation which dictates the evolution of the quantum mechanical system, or you can say quantum mechanical state with time, and how to assess various physical quantities in context quantum mechanics. Okay, so for example, one has to understand that I'm going to deal also, and that is quite people find it very difficult to understand. But as I promised, parallelly I'm going to run lectures of linear algebra, and I'm going to just try to make you familiarize with all these kind of concepts. But right now, you need to understand that I haven't taken a postulatory approach. So right now, first, our focus would be to understand how to do quantum mechanics, and side by side, I'm going to develop an approach using linear algebra, which will make you understand to a level depth that how these things are actually working. Okay, how these things are actually working. Okay, but first we'll actually try to do some of the quantum mechanics using some of the potential problems, and by just keeping in mind all these postulates. So this is how this is what I mean from the quantum mechanics. Okay, so I hope to meet you in the next lecture with the postulates of quantum mechanics. Okay.